Hey everybody, welcome to this lesson on binary. If you're a teacher looking at this, why might you use this and want to teach binary to a class? It's useful because it really gets students thinking about the number system that we use, the decimal number system, and seeing that there is other number systems out there. It's pretty accessible to students, I'd say probably from middle school and up, but some younger students can understand it too if they have a strong grasp of mathematics. It basically just uses some addition and multiplication and a little bit of powers. So it gets students thinking about numbers. As a student, what are our learning goals for this lesson? The first would be to understand what is binary. Right? What exactly is it? And then the second would be how to convert between binary and decimal numbers. That's pretty much what we'll go over today, and then talk about maybe why binary is useful as well. But let's start off with a joke. There are only 10 types of people in the world, those who understand binary and those who don't. If you're laughing right now, you probably understand binary. If you're sitting there scratching your head, you probably don't understand binary. But by the end of this lesson, hopefully everyone will be laughing along with this hilarious joke. So let's start by thinking about our number system, the decimal number system. So we use what's called a base 10 number system. So we have 10 digits. Think about this. This is pretty cool. Every number we have can just be made up by 0, 1, 2, 3, 4, all the way up to 9. We can make every number just using those 10 digits. And you probably know that we have place value to help with that. So we have our ones, we have our tens, we have our hundreds, we have thousands, and so on. Right, 10,000, 100,000, millions, and so on. And what's interesting about those is every single one of those place value amounts can be written as a power with base 10. So 1 is 10 to the exponent 0. 10 is 10 to the exponent 1. 100 is 10 to the exponent 2. 10 times 10 is 100. So our next place value is 10 to the exponent 3, which ends up being 1,000. So our next place value is 1,000. So we can make up every number just by using those place values. Let's erase this for a second and let's show a specific example. So the example here is write 8,456 using base 10. So let's break this number apart. We understand that this 6 is 6 ones, right? This 5 is 5 tens, right? This is 4 hundreds, and this is 8 thousands. Right, so we have 8,000 plus 400 plus 50 plus 6. We can break that apart even further, so that's 8,000 is 8 times 1,000 plus 4 times 100 plus 5 times 10 plus 6 times 1. Can fit that 1 in there maybe. Ooh, that got out of hand real quick. There we go. Right, and we just saw there that 1,000 is 10 to the exponent 3. 4 times 100 is 10 squared, plus 5 times 10 to the exponent 1, plus 6 times 10 to the exponent 0. So we've written this in expanded form with base 10. So 8,456 is 8,000 plus 400 plus 50 plus 6, which is 8 times 1,000 plus 4 times 100 plus 5 times 10 plus 6 times 1. And we saw that our place values of those ones, tens, hundreds, thousands, 10,000s can all be written as powers with base 10. We use base 10 Can you think of why we might use 10 as our base? Why is that a nice number for us to use? Think about that maybe for a second. If you're looking at your hands right now and counting 10 fingers and thinking that that's the reason, you would be correct. Right? We like 10 because we can count with 10 on our hands. So using that as our main number system makes sense. But that's not the only base that we can use. The ancient Babylonians and Sumerians, they used a base 60 number system. And you can see here, they used symbols, right? So they had 59 of them. So base 60 would repeat after that. Our number system on our clocks also uses the same base 60, right? After 60 minutes, it repeats, which can make adding and subtracting times difficult, right? Because it's not the same as tens and hundreds. There's others that are really useful. Hexadecimal is really useful for color codes in web design. And what we're going to talk about today, binary, zeros and ones, is useful because it is the language of computers. So that is why binary can be important. When we code computers, we can write in a programming language, but we often we want that converted to what the computer can understand, right? Computer, we can't just say, computer, do this. Computers understand a different language, and that language is binary. They understand zeros and ones. So we can tell a computer what to do in a coding language. It compiles it into zeros and ones for the computer to understand, because computers are electrical machines. They understand basically zeros and ones on and off electrical circuits. So that's how they understand language. So that's kind of why binary is important. You don't really need to know binary in order to code, but it can be useful to understand, and it helps in our understanding of mathematics and number systems as well. Okay. So when we used our base 10 number system, every place value was a power with base 10. Right? So we had tens, hundreds, thousands, tens, hundreds, thousands, tens, thousands. In a binary number system, we replaced that 10 with a 2. So instead of every number, every place value being a base 10, it is now base 2. So instead of tens, ones, tens, hundreds, thousands, we have 2 to the exponent 0 is 1, 2 to the exponent 1 is 2, 2 times 2 is 4, 2 to the exponent 3, 2 times 2 times 2 is 8, 2 to the exponent 4 is 16. You can probably see the pattern, we're just doubling every number. So 16 times 2 is 32. The next one, 2 to the exponent 6, 32 times 2 would be 64. You may have seen these numbers. These are doubling numbers. If you ever played the game 2048, you might recognize those numbers. So instead of having base 10 number system with ones, tens, hundred, thousands, we now have this new number system where we have place values of 1, 2, 4, 8, 16, and so on. So everything is changed, right? And in our decimal number system, remember, we had the digits 0 through 9, 10 digits. Binary means 2. So we only have 2 digits. And those digits would be 0 and 1. So we can make up every number in the binary number system just using the digits 0 and 1 instead of 0 to 9 like we use. Probably one of the best ways to learn this is by looking at an example. So let's look at an example of converting from binary to decimal. So let's look at this number, 1001. Note that this is not the number 1001. I could put a little 2 there to show that it is base 2. This is a binary number, 1001. But we want to convert it to whatever it would be in our decimal number system, base 10. So I find it useful to write out a chart when we're doing these. And instead of putting in ones, tens, hundreds, thousands, like our decimal number system, we'll put in our new base 2 number place value. So 1, 2, 4, 8, 16, 32, 64, 128, 256, and so on. And what I'm going to do is I'm going to write my number underneath. So 1, 0, 0, 1. So let's see what the value of this is in our base 10 number system. So this first one, what is its digit worth? Well, its place value is 8. And this 1 means that it's turned on. We're using that. So this is like 1 times that 8, or 2 to the exponent 3, right? Plus 0 times 4, plus our place value 0 times 2, plus 0 times 1. Notice this is similar to what we did when we broke apart this base 10 number, right? 8 times 1,000. We have 4 times hundreds. We have 5 times tens. Here we have 1 times 8, 0 times 4, 0 times 2. And this should be 1 times 1. Catching my own mistake. So that means 8 plus 0 plus 0 plus 1 is 9. So the number 1001 is the number 9 in our decimal number system. We have the 8, we don't include the 4 and the 2 place value, and we have the 1 place value, so it's worth 9. Let's look at another example. So let's write it underneath. Okay. So we have the 16 place value we include. We have 0 for our 8, so we don't need to write anything. We have a 4, 1 times 4, 1 times 2, and 1 times 1. So if we add all those up together, 16 and 4 and 2 and 1, we get 23. So the number 10111 in binary is equivalent to the number 23 in our base 10 number system. What about going the other way? What about converting a decimal number to binary? This is a little bit harder. I made this little flow chart. Maybe that makes it a little more confusing for you. I don't know how your brain works, but we'll kind of follow along with it. So the first step here is to go to the largest place value possible and make it a 1. So if we wanted to convert the number 53 to binary, what's the largest place value we could have? Well, 64 would be too big. So we'll go to the next one, 32, and we're going to include it. All right, and we're going to keep a running total as we go of where we're at in making our number. So far we're at 32. We've included 32. Next step, go to the next place value, add it to your running total. So we're going to go to 16. All right, so now my running total is 32 plus 16, which equals 48. So now my running total is at 48, but we got to check, did we go too big? Well, 48 is still less than 53. So if our running total is bigger than our number, we don't want to include that digit. Right? But if it's less than our number, we want to include it. So if I include the 16, I'm still under my goal of 53. I'm at 48, so I'm going to include it. Let's go to the next. If I include my 8, I have my running total, I'm going to call that RT now, which was at 48 because I've included the 32 and the 16. 48 plus 8 would be 56. But that's too big. We only want to make 53. So that means that I don't want to include my 8. So I'm going to go back here, and I'm going to make this a 0. Because if I include it, it's way too big. So we're still at 48 for our running total, 32 and 16, but not the 8. So let's go to the 4. 48 plus 4 is 52. We're still under our goal of 53. We're only 1 away. So you can probably see now that of my last 2 digits, my 2 and 1, I'd want to add 1 to it to get to 53. Because 52 plus 1 is our goal of 53, which means I'll make my 2 a 0. I don't want to include that place value. So 53 would be 32 plus 16 plus 4 plus 1. 48 plus 4 is 52 plus 1 is 53. So that gives us the number 110101 being 53. And it's kind of interesting that we can make every single decimal number in binary. So just using the digits 1, 2, 4, 18, 16, 32, 64, 128, so on, we can make every decimal number, which is pretty cool. So let's do a couple examples here. Let's make 27. So the largest place value I can use here, 32 is too big, so I'm going to include the 16. do my running total up here. We're at 16. If I include 8, we're at 24, which is still under, which is good. So I'm 3 away. So that means I want a 2 and a 1. Right? Because 16 plus 8 plus 2 plus 1 will give me 24, 26, 27, which is my goal. So I'll make my 4 a 0. So the number 27 in binary is 11011. Let's make 151. So the biggest one I can use is 128 there. So my running total is 128. If I'm at 64, that brings me way over, so I'm going to make that a 0. But if I include 32, that gives me, well, that would be 160, wouldn't it? Which I only want to get to 150. So 32 is even too big. So we're going to make that a 0. But 16 I can use. 128 plus 16 is 144. So I can include my 16. So now my running total is 144. Okay, so running total equals 144. Let's include the 8. So 144 plus 8 would be 152. So that's too big. But I can include my 4. That would give me to 148. Plus my 2 would bring me to 150. Plus my 1 would bring me to 151. So 128 plus 16 plus 4 plus 2 plus 1 is 144. 148, 150, 151. So the number 151 is 100101111 in binary. A little trickier one to make. So let's go back to our joke at the beginning. There are only 10 types of people in the world. Those who understand binary and those who don't. And here is the crux of the joke here. This isn't really a 10, is it? It really is the binary number 10, which would be, remember our place values are 1 and 2, so this would be equal to 2 in our base 10. So really it's saying there are only 2 types of people in the world, those who understand binary and those who don't. It's just saying it using the binary number 10 instead of the decimal number 2. You can all go ahead and laugh now. So that is our lesson on binary. Hopefully now you understand what binary is and why it's useful, and you can convert between binary and decimal numbers. But I encourage you to go practice, because that's really how you can understand it. And if you want to find out some more great math content, please check out Math Fun 101 on Instagram and Facebook.